I'm Lubensky now, and he's gonna talk about, let me see.
You ready?
Yeah, we're ready. Go ahead, Tom.
Okay.
Thank you.
Okay, today's going to be a little strange. I made the mistake last night of defining a better way of presenting things, and then I didn't have time to put it in order. So it's going to be a little haphazard today. I'm going to finally broach the topological lattices. We'll start off with the Schrieffer-Heeger model, and then discuss the various Kagame lattices and their variants. And then I'll probably have a hodgepodge of topics that will involve switching between different PowerPoint slides. So here we go. So I'm going to talk about the topological index and edge states in the Schrieffer-Heeger model. I'll mention a mechanical version of that, which I won't talk about much. Then I'll do the Kagame-based lattices with distinct topological properties and topological counts and edge states in Kagame-based lattices. Then I will probably talk about, just mention other things that have been done that are, for example, we'll look at some square lattices that have what are called Weil modes. I'll present a little bit of information on some random systems, if I can find it. But we may end up going home early today. We shall see. Okay, so polyacetylene is a polymer which has usually, you can think of this as being the carbon atom, and these are two carbon atoms, and their hydrogen atoms come off the edge, and they spontaneously undergo a transition in which you have a unit cell consisting of the blue and the red site, and these bonds have different strength. So if I'm talking about the electronic states, it hops more easily from this to this than it does from that to that. But nonetheless, this has modes that have zero energy that are started at either end, depending upon the conformation. And you can have solitons, which take you from a state A, where we have the double line on the right, to one where you have the double line on the left, and the price you pay is to have two single lines in the middle. Or you could do it the other way around and have two double lines and have surface states. So here's the mess. So that the Hamiltonian, the Schrieffer-Heeger Hamiltonian can be written like this. I've been a little sloppy in this case. I didn't worry about whether I'm using fermion equations of motions or not. I'm just treating these as scalar fields at the moment, or we're not doing any real statistics, so we don't have to worry about it. So we have a going back to the previous slide, I'm going to call the single line weak bonds as V1, and the hopping elements are V1, or V2 for the double line here, which means that it's a stronger thing usually. So we have V1, psi dagger A, B, psi B on the same site S. So again, the sites are the blues and the reds, and the lines are the bonds. So we can change a B state to an A state, or hop. Really, I can hop from an A to a B, or a B to an A. You can go either direction. And these are notice that there is no, this is on the same site, but a given A site can communicate with a B on both sides, and a given B site can communicate with an A on both sides. And then we have the V2, which I've arbitrarily assigned a negative sign. You can do that with electronic things, not so much with phonon type stuff. And so here we have that we kill an excitation at site S minus 1 and create it at site S, or the other way around, we kill on state an A site on state in the S unit cell, and we create a B at the S-1 unit cell. So you can see how that is going back here. This guy can, hop from there to there. In the process, what happens is, you lose the fermion here, or you lose the particle here, and it jumps over to there. Or on the other hand, it can go this way, and the rates going in the two directions are different. But no blue atom communicates with a blue atom, or a red atom with a red atom. They have to go through the intermediaries. Oops, wrong way. Okay, so this, which is written out in its simplest form, can be written as a two-component field times a 2x2 matrix, which we can express in the format of the Q's and C's of the mechanical models we've been looking at. So here we have psi dagger AS, QSS prime. We can go from S to S prime, psi B, and then psi dagger SB, which is the other way around, psi S, and we can write this as a psi dagger of Q, HQ psi, where the H is a 2x2 off-diagonal matrix, including the V1, which allows you to hop from where you stay in the same site when you hop, so this is the same unit cell when you hop, and you have the ones which take you from S prime to S-1, or S prime to S+1. And we'll call the one that's up here the QSS prime, and the one that's down here is the CSS prime. And they are, in fact, what do you call it, transposers of each other. So we can take a Fourier transform and write C of Q as V1 minus V2 e to the IQA. So Q is the wave number, and A is the lattice spacing. So HQ can be written as C star C. And we should observe that if you square this, you get C star and C star C along the diagonal with zeros on the off diagonal. So this is an easy problem to calculate the energy for. The energy is just the magnitude of C of Q, which is V1 minus V2 squared, 4V1 V2 cosquared QA over 2. So you can see that if we choose the V1 equal to V2, which means that we don't distinguish between the right and left hoppings, we get square root of V1, well, square root of V1 squared times 4 times cos squared. So the energy is plus or minus V1, because we times cosine of Q2 over A, and this is equal to 0 when QA is equal to pi, because cos pi over 2 is 0. So the energy spectrum, we have two bands, the minus band and the plus band, and when we set V1 equal to V2, we find that we have the crossing of these bands, and there is what's called in some instances a Dirac-like point.
I have a question, a quick question. Are C and Q the compatibility and equilibrium matrices that you talked about before?
In fact, the arithmetic for them is essentially identical, as it is for the others. So this is, in a sense, a one-to-one correspondence. In fact, I'll briefly talk about a mechanical model that gives the same thing. So yeah, you're perfectly free to think of them like that. The only difference is that this is one-dimensional, so it's a simpler problem, but it has all kinds of sign confusions that I was fighting this morning. Anyhow, this is C star and C, and so we can go from an ungapped to a gap situation, and we can also go from V1 greater than V2 to V1 less than V2. The spectrum doesn't matter. It's just the wave functions that'll be different. So I can access this point with the gap, which is proportional to delta V. It's twice V1 minus V2. Okay. So we know what all of the excitations are. Well,
there is another question here, Tom. Let me
pass
the microphone.
Tom, can you hear me?
Yes.
Thank you. A question about the model. Why is there no self-interaction? I didn't quite catch. Why is there no AA terms or a BB term? Psi dagger A, psi A, like a number.
Why isn't there a psi A, psi A?
Psi dagger A, psi A, for example, a number operator for the excitations.
Let's go back to the model.
Yeah.
Oops, wrong direction. So the model is this. I have, you know, a red site and a blue site, and, you know, there's a whole, you know, each unit cell consists of two sites and two bonds. So, you know, I'm drawing a circle around one version of the unit cell. Now, I could also have the unit cell the other way around, where I have the double line to the left and the single line to the right, and over here I have the single line to the left and the double line to the right. So those are both acceptable unit cells, and, you know, if you have periodic boundary conditions, you can, you know, it's totally arbitrary. It doesn't matter which one you're doing. But when we get to the surface states, then, you know, it can hop easily in this direction if it starts off with a simple hop on the lower energy, and it has trouble hopping back in the other direction. So we'll spend a little bit of time, and I hope I don't confuse you when we talk about the surface states and a little bit on the what do you call it? Domain wall here. What's a topological domain wall? Is that clear enough?
Yes, Tom.
Yeah.
Thank you.
Okay, so here are the equations of motion, which I calculated simply by, you know, taking delta H delta psi dagger and A and delta H delta psi dagger B, and that gives me these equations. So doing that, the equation is CSS prime operating on psi itself is equal to V1 psi AS V2 psi AS plus 1. And notice now that this comes from differentiating with respect to the B site. And when you differentiate with respect to the B site, you get the two A sites that are connected to it. And then this is equal to E times psi B, because, you know, that's how I calculated things. Similarly, I can take the derivative with respect to A dagger, and I get a psi BS prime is V1 BS minus V2 BS minus 1 in the opposite direction. And so, you know, when we look at the surface modes, we'll find that we have sort of opposite behavior for the B and the A. So let's just write out this equation. Now what I'm interested in principally, I mean, we have all of the energies, you've seen them there, but what we're interested in are there any modes with zero energy? So let's just put E equal to 0 over here. And in doing that, we decouple the A's from the B's altogether, and we have an A lattice energy, you know, equation, which says that VA at site S plus 1 is V1 over V2 times VA at site S. And I can repeat that again and again and again. So I get psi AS is V1 over V2 to the S times psi A0. Now, the way I'm thinking, as I increase S, I move from the left to the right. And so now you can see we've got a solution right here that allows us to have an edge state with zero energy in which psi A dies off exponentially as we increase S, so long as V1 is less than V2. Now, if we made V1 greater than V2, then of course we would grow exponentially, and that's not something that can go on forever, right? So this provides us with a zero mode that is located on the S site. Or I can look at this equation and look at psi S minus 1 is equal to V2 over V1 times psi AS. Now, what this tells us is I can look at what happens as I move from the site in at the far end to the right, which means I ask what is psi A at n minus S, given that I have a psi A at n. And here we have that if V2 is greater than V1, then you know, we're in trouble. We can't do anything. But if V2 is less than V1, then we've got a mode that's going in the opposite direction. It's a zero mode that starts on the right and goes to the left. So what we'd like to do is to establish, down here, we have a cartoon of what happens when T1 is less than T2 and what happens when T2 is less than T1. Now, the goal of this is to try to cast this really trivial observation in terms of something that's at least, comically uses the formalism of the topological system. So is this something topological? Incidentally, I should have said, I reminded you that we could also have taken derivatives with respect to A, and then we have the same equation, except that we have A here, and rather B here and A on the other side, and you can then calculate, notice, because the B is unconnected to the A, the zero modes have the peculiar property that you can have the mode die, in which it is only the second atom, rather the first one that moves. So it starts off at 1, it sees that the atom 2 in the sequence, it doesn't move, and then this guy moves down. I mean, we can basically ignore what's going on in the B lattice.
We have another question here, Tom.
This way, except that
we have another question
here. If we turned it around and made V2 less than V1, then again on the A site you can get the decaying mode.
Hey Tom,
okay.
We have a question. Let me pass.
Okay, so we've shown that there's a zero mode on the right hand side if this is font problem again. I used Times New Roman, and it likes to call an italic V a new. Okay, so this is V1 when V1 is less than V2 in magnitude. It doesn't matter what the signs are. Then we know we have a zero mode. It's what? No, actually, this is the left-hand side. Yeah, okay, we'll leave it like that. This is the left-hand side. So the outer normal, so now I want to start couching this in the terms that we will use when we talk about the Kagame lattices. So if I look at this, the arrangement, the normal to the left-hand surface points in the minus direction, the minus x direction. So we can say that, to think of this, you have a whole string of these, and I have a surface that runs here. Then when we characterize the different planes in the lattice, they are indexed by the reciprocal lattice vectors, and their sign is that they are perpendicular away from the surface itself. So G is equal to minus B, where B is a vector that points in the x direction. So B would be one of the fundamental reciprocal lattice vectors. So let's start off with what we know now is that NC of B, so this is associated with the B lattice. So it's whatever NC is. If I'm talking about the wave number, rather the site being equal to B. So that's equal to 1 for G equals minus B for the left edge. And so we can define a vector which is minus A, where A again is positive if it's going to the right and negative if it's going to the left, and its length is equal to the length of the bonds, which we will treat as all being equal in length here. That's not quite true, but it's not worth trying to figure that out. And then, so crudely what happens is that C of Q, as a function of Q, that this B is a fundamental vector of the reciprocal lattices, so this is really a Q here. So if we've said that G is minus B, and we want to calculate NC of B to be equal to 1, that means that we need a 0 in the unit circle. So if we write C of Q as magnitude C of Q e to the minus I Q dot RT, if we come in and replace RT by A with a minus sign, and the Q with a minus B, then we get this as just e to the minus B dotted into A, and that is what we want, and we'll get a 2 pi factor that comes out here. If we go to the, so we're talking about the left edge here. So NC of G is plus 1 for the left edge, and it's -1 for the other side. So NC of G is G dotted into RT divided by 2 pi, and the 2 pi cancels the 2 pi that's in the G here. And then for the right side, we can have an NC of G, which is the opposite. So what happens is you can think now of the phase of the C of Q as being minus Q dot RL plus RT, where RT is what we've just calculated. It's the minus A. And for the left-hand lattice, we are set up so that this is equal to 0. And so phi Q is just minus Q dot RT. But we want to look at the other side, and there we want the number of 0 modes to be 0, as we found out when we use this, that then we can write NC of B is the minus B, because we have a minus sign up here, dotted into what we'll call a local topological number. So RT is, we'll call that a reference one. This is the value that comes out of doing the integrals that produce the topological variables. So we'll take the model, or the reference unit cell is the one where I go from blue to red with the weak bond between them. But now, in order to describe what goes on to the other end, the B switches directions because the surface normal is out like that. And so we have a minus B here, and RL and the RT. So the RT stays the same. That is the minus here. So we get a minus coordinate there. But RL is really what it is it changes the unit cell. So RL, rather than having the unit cell be, well, this particular one, I had the unit cell starting with the double line and having the smaller, the narrower line on the right. But if I start off and call this my unit cell, and I move along to the end, then if in order to, what I want is a unit cell that is compatible with the surface, that I don't split the unit cell into 2 by taking, by cutting, right here, for example. So what we do is we do a transformation that takes this point to that point, and now we've got a unit cell that has the narrow line with a weaker bond connected to blue and to the left. And so you can see that going this way, starting with the blue atom, is the same thing as going the other way, starting with this blue atom. Okay? We can go around and around in circles here and get confused. Okay, so how do we calculate the topological charge of the gap states? So, as I said, I decided I was going to change things in the middle of the night, and now I have some notation that is different. I changed the sign here, but we've discussed that the sign doesn't make any difference. I've called it the V, the T, and QA is K. So anyhow, this C of K or C of Q can be expressed as Z of a complex number, and you can see that it has a 0 at Z equals minus T1 over T2, so that if the magnitude of T1 is less than T2, there is a 0 to the C of K that occurs within the unit circle. So you can think of it as plotting imaginary versus real K as shown here for the case when T1 is less than T2, where we know that we've got a 0 inside because we know we have a 0 mode there. So we wrap around here and we find a 0 along the real axis, and the center of the circle is at T1 over T2. Now, what this means has to have happened is that the phase of C has to, it can either go and come back as I go along K, and because we're on a periodic lattice, it repeats itself. So a function on this lattice can go from 0, come back to 0. That's the case where I don't have any poles. When I have or zeros, when I have a 0 in the middle, then you can actually, calculate the phase of this quantity, this whole quantity, and ask Mathematica to calculate it for you, and it goes from 0 up to 2 pi. So we have various ways we can deal with this. We can calculate the integral of g prime of z over g of z for any function g. This is the famous Koshy, I forget, it's a Koshy theorem. And what that says is that this integral around the unit circle gives you the number of zeros minus the number of poles in the function g of z. So it's something that has to just have integer values. And of course, this is the same thing as the derivative of the logarithm, and I can write it like this. So rather than doing an integral around the complex plane, I can go from 0 to 2 pi along a particular direction in the space. And in our case, there's only one direction. So it's dk, d by dk. The log of g is I times the exponent here. And the exponent is whatever you calculate by calculating the imaginary part of this guy. Or you can calculate the phase of this guy. It's basically sine k over t2 over t1 minus t2 cos k or something like that. So if we have only zeros, then nu would be equal to, this would be equal to 1 or 0 or 2. But since we have just a linear equation here, we can at most have 1 0, and we don't have any infinities in there. So that's how we calculate the phases. And let me see, did I? Yeah, okay. So what this is telling us now, and then we want to remember, is that if you start, that the surface states are getting a hold of them, requires understanding what the unit cells are at the edges. And what goes on depends upon what happens here. I could have terminated on the red site, and then I would have had, only half a unit cell here, and we'd have to be careful about how we treat that. Okay, so one can also have domain walls, and you can see how we've done it. We have the red, blue, so weak, strong, weak, strong. This is the one where we have, if I were to just cut here, I would have only going in the positive direction, and we would have the same 0 mode that we had if we just terminate the cell here. At the other end, we go backwards, which is the same thing, but again, the sequence as we go to the left is red, blue, et cetera, instead of blue, red. And, for the H-bar physicist, the Hamiltonian we had is invariant. Rather, when we go sigma, we do this transformation with the sigmas. These are the Pauli matrices. You take h to minus h, which tells us whenever there is an e, there is a minus e, and that tells you have to have a gap, which of course we've calculated. Okay, so here is this is the cartoon of the mechanical Schrieffer-Heeger model. Let me have a glass of water here. Oops. Okay, so what we want to think about is a bar that has rigid rods attached to it that are attached to a spring. And you alternate the direction of the rods as we go along. And so here we have the case where the springs are equivalent, and that's like the Schrieffer-Heeger model at the critical point. Now, what we can do is to introduce twists to these lattices, and you can allow them to, have a starting point, which is something like this, and then we can ask about the vibrations relative to it. So, is there a question?
No, Tom.
So see, we alternate directions of the tilt, and we stretch the lattice. We stretch the springs doing this. So we can have, as before, we can have solitons, if you wish to call them that, or localized excitations, grain boundaries in the center, and they can be either the single or the double. Now, you can set things up so the change in length of the bond is the compatibility matrix times the change in angle at the site S, and beta refers to the bond that is adjacent to S. And you can also look at what happens on either side. This is like the psi at site S, and this is the psi at site S plus 1. And you can Fourier transform, and you get something that looks exactly the same as we had before with a C1 and a C2 and an EVIQA. The only thing is now the real part of this lattice is much more complicated, but it can be dealt with. And you can go through the analysis here, and you get exactly the same thing that you get for the Schuh-Schrieffer-Heeger model. So you can calculate that as. Okay, now I want to move on to the particle. The Kagame lattices, the topological form. But first, I want to show this marvelous movie of a model system that shows in mechanical detail what we're going to predict are the properties of the lattices. So this is due to Rocklin, Zhu, Sun, and Mao. And that Mao is Xiaoming Mao, not the other Mao. Okay, so let's watch what happens here. This worked before. Yeah, okay. So they created a Tinker Toy thing here. You can vaguely see that we have the pattern. It's structured in such a way that you can't easily see some lattice lines, which I'll talk about. Now notice he's pushing this, and the whole apparatus is not moving with respect to the table, but he did invaginate on this side. Now he's going over to the other side, and the same thing happened. In other words, the two sides have equivalent zero modes. Now they're going to introduce a transformation, which is going via the Guest-Hutchinson mode past a critical point, which they will indicate here. Okay, so this line is equivalent to the straight lines of the untwisted Kagame lattice. It represents a transition between one topological class and another topological class. And so now that they've got it all set up, we're going to invaginate again, or try to, and see what happens. So he's going to push. It's not invaginating. The whole lattice is moving, which says that we have no softness on this side. This side is rigid. What happened? Well, let's look at the other side. See, he's is able to push in harder and go further. And recall that nothing has happened to the Maxwell counts on this. We still have the same coordination number, the same number of cut bonds to free the system from the periodic boundary conditions. So, what's happening must have something to do with when you change the topology of these bonds, you change the topological structure, and you move a bond from the bottom lattice, a zero mode from the bottom lattice to the top lattice. And so there are two zero modes per unit cell on that side and zero on this side. I should mention that, he's able to invaginate basically on a single cell. And what that means is that, to get a point distortion, you need all of the vectors, Q vectors in your reciprocal space. So what we're seeing is that we have 2 zero modes per unit cell on the surface on one side and none on the other side. And if we were to reverse the guessed Hutchison distortion, we would go back to having the, having the two sides equal with 1 zero mode per unit cell, and they could keep on twisting in the other direction and get the two. So you can actually cycle all the way through. So we want to see how that comes about here. So what we have to do to make progress, or at least it's a good idea to make progress, to relax the constraint that the Kagame lattice that we want to start with and play around with is not the standard isotropic Kagame lattice here, this one, which has a C6 symmetry, but to arrange things so that we have the straight lines of bonds only in one direction. And so that means that we have these states of self-stress that are horizontal, no states of self-stress that are vertical, and we can continue this operation. So this guy, we can go from here to here by taking this site right here and moving it upward. See, that creates this. And of course, I do it on every one. That goes up, and it does it on all the sites. Or I can come along and take the same site and move it down, and that's what happens here. But in the process, I'm allowing the triangles in the lattice I'm looking at have a different shape. And this guy, notice, really is not, it's hexagonally symmetric. Well, it isn't quite hexagonally symmetric. I won't go there. But you certainly change the cells here. So the question is, how do I go from here to here? And it's sort of amusing. What you can do is you start off with something that looks like this guy right here, this guy right here. And notice that we have, oh, it's a little unfortunate. I've drawn the picture so, I mean, strictly speaking, what we've got mapping here is this guy is the same as that one. So think of it just inverting this thing and turning around, pointing it in the other direction. So here we have, we start off with an equilateral triangle or one that's almost equilateral here, a triangle like that. So that's the system we start with the straight line. The dotted lines are straight lines going all the way through that have, support states of self-stress if they're there. So what we're going to do is to move this guy downward. That immediately gives me a kink here, and I lose the state of self-stress. But in the process, if I do that, I keep the point on the straight line here. And what I want to do is, when I'm doing this, is to move things so that only this line right here, gets distorted away from the straight line. And then I can do the same thing in all three directions. So you can take, we have, the unit cell has 3 sites, 1, 2, and 3. And what we need to do is to move those sites so that we get that structure. So we set R mu, mu labels the sites 1, 2, and 3. And we let P be the directions of the reciprocal lattice. So the lattice itself, we're thinking of A1 as being along the horizontal axis, and the triangles that are go with the hexagonal lattice are the A2 and the A1. The reciprocal lattices point with the starting with a vector pointing upward, and the other two completing the triangular arrangement down here. So with each of those, I can do that. And what you can show is that you can look at this as a function of x1, x2, and x3. So here we have parameters x1, x2, and x3. And for simplicity, we're leaving out the z, which has this p mu minus 1. So r mu is the original r, x mu, p mu. So in other words, it's moving upward like that. X mu minus 1, a mu plus 1, so that if it were the 1, it would have a direction like this, and then we ignore this one. But we do constrain x1 plus x2 plus x3 to equal 1, and we have a phase diagram where in the center we have the non-topological business. And on the edges, we have topological versions in which the blue arrows indicate the directions of the generalized RT, the vector that characterizes the reference cell that we're talking about. Okay. So, back to this, we can now look at surfaces, and we index the surfaces by the reciprocal lattice vector that is normal to them. So you can see, recall from solid state physics, you have all of these surfaces which are lines of atoms, and you can make different lines with an increasing length here and a decreasing magnitude of g in the other direction. Is that right? No, I mean the g also increases. So g is 2 pi over a, and then it becomes 2 pi over b, where b is the new distance. So yeah, so g does get smaller. Now we have choices for the unit cell. We can make all kinds of different unit cells, just as in the into the SSH case, where we had the double line is to the left and the single line to the right, or the other way around, or two different versions of the unit cell. Here we have far more freedom to make things. So here are two symmetric cells, where one we put all of the three lattices on the triangles. So the orange are the actual three atoms in the unit cell, and the yellow ones participate in another unit cell. So we have 3 atoms and 6 bonds per unit cell, and that means that this thing is, as we started with, it's part of a Maxwell lattice, because we have twice as many bonds as we have sites, and that's true at the microscopic level as well. Okay, so how are we going to think about this? We start off with this unit cell here, the red one, which has a 1 next to it. So this one, it is characterized by an RT, but it's really not so comfortable as a surface unit cell. So let's look at some of these surface unit cells. Here's a surface unit cell. How do I get from here to here? Well, I have this triangle is there, all right. That one's okay. And we have this bond, that's okay. So this bond and this bond have to be moved, and we have to move them by a distance which is part of the primary translation vectors of the lattice. So this guy I can move to here, move this guy to here, move this guy over to here. So this one is moved in the A2 direction. This one, which is down here, has moved in the A3 direction. And now have I got them all? I've moved these two, yeah, so I have closed the, no, actually I did that slightly wrong. This guy goes up to here, and this guy goes over to there, right? And then I've constructed a cell that looks like this one. So we have an RL, which is, it's, I'm only moving bonds. The bonds have single charge, the sites have double charge. So when I move this bond, it's going along the vector, well, we can go back again. It's going along the, it's going along A2, and the other one is going along A3. So this is along A2, and this one is along A3. Okay, so that means that we have here that the translations set is A2 plus A3. And so we have to add that. We don't have any site movings, but we have the R moving. And so what we have to calculate the topological charge in this case is the G dot RT is the topological value which we had, which is equal to 1 for this G, which is going outward. And now RL depends on the transformation, so we have the G RL plus RT. And now how did I do this? Right. So here are various examples of what can happen. So the first one we looked at, RT is equal to minus A1. You can see it's pointing in this direction. And we calculate that by calculating those topological integrals, which we just discussed. RL is, oh, I'm sorry, I missed something here. Let's go back. Yes. And so also I have the site moves from here to here, right? We instead of having the 3 sites around the triangle, we have the site here. So this guy gets multiplied by twice this vector, which is the A2 vector. And this guy gets moved by the, no, I'm sorry, it's this site that gets moved, right? This site goes from here to here. Notice there's no site there. So this is A2, and this guy is also A2, it looks like. Oops. No, that one was A3. So let me just get the A3 correct. A3 is moving. Oh, it's minus A3. It's minus A3. That's what it is. Yeah, minus A3. So this is 2A2 minus A3. So it's A2 minus A2 is A2 plus A3. And A2 plus A3 is oops. Shoot, how do I have to go here? Go back. Yeah. So you can see that A2 plus A3 is minus A1. So now that actually this gives me that G dot A G, which is the normal here, is G2 minus G3, which is off like that. So it's pointing in the X direction, and that's equal to 4 pi over A minus 1, 0. So the number of zero modes that we have is equal to G dot RL plus RT divided by 2 pi. And you can see that that is indeed what the case is. We have this A1 dotted in the vector that's twice the G that goes that way. So that product is 2. And we get then that we have 4. So how do you characterize these zero modes? We have 4 different modes that have 0 energy or a decaying mode from left to right. What we plotted here is the inverse penetration depth. In other words, we've converted the QY into an I kappa so that we have an exponential decay with an e to the minus kappa there. And so here are the parts. So this guy turns out to be doubly degenerate. The green merges with the KR, with the blue line at large distances, and they become sort of also degenerate. But this was a calculation that actually came from. You know what? I think I forgot to. Just for the heck of it, let me see if I remember to do what I should have done. No, I didn't. I didn't draw the thing. I wish I could go to the blackboard, which you can do when you give a straight one. So the way these are calculated is that your whole matrix, the C matrix, has C11 along the diagonal, and right next to it, there's a C12 along the displaced diagonal. And so you have an equation which is C11 plus lambda C12 equals 0. And that's true all the way down the line. And from that, you can extract the zero modes. Okay, so this one now, the G is pointing downward. RT points in this direction. And this one really is the classical case. You only have two solutions, two of these. So I have, two different KRs versus QR. So there are two, and both of them, well, no, the dotted line here means that it's on the opposite side. Now this one is amusing. We have three modes on one side, and I'm sorry, this is the one that has the two modes per unit cell only, which is the same one that you saw in the picture in the movie, where there are two modes on one side and none on the other side. This also is none on the other side. This one, with G this way and RT this way. So notice that the overlap of G and R is smaller here, but the sort of unit cell we have, aside from the shape of the triangles, is really essentially the same as that. It's the blocking one here. So what happens is the G dot RT, the extra component along here, gives us a extra count of 0 modes coming in this direction, and there are 3 of them, and here there's 1 on the other side. Yeah. So I should point out that one thing that's happened here is that we have 1, 2, 3, 4, 5. Let's see, 1, 2, 3. Okay, I'm drawing a 0 there right now. It's what we actually have more sites per unit cell in this direction. So 1, 2, 3, 4, 5 sites. So the ones, these guys are not, So it's 1, 2, 3 this way. Okay, right. But the length of the cell is larger. Okay, that's the best way to state it.
Hey Tom, can I ask a quick question?
Sure.
If you show the plot that you were looking at before for KR.
Yeah. I'm sorry, I'm going the wrong direction. Kappa R, yes?
Okay, kappa R, yeah. And this is an inverse penetration depth, you said, right?
So what the wave function for this state, it is e to the minus kappa R times x.
Got it.
Times e to the IQY, QX, QY in this case, I guess, the way we're drawing it, e to the IQY along the vertical thing, and e to the minus kappa R.
And you have a negative solution for the orange curve?
Well, if we have a negative solution and your boundary conditions are right, that says you have a wave decaying that direction.
Okay,
okay.
Okay, it's not a big deal. Okay.
Right. Yeah.
Got it, thank you.
Let's see, I wanted to say something about, oh yeah, I forgot to point out the unit cells here. So, here is a unit cell which has the 3 things, and it is, I can make hexagons out of it. Now, to get from here to an equivalent site, I have to go a larger distance. So this thing actually, has the G vector or the volume of the unit cell has been changed. And that actually plays a role in these calculations. Okay. So you can see now how RT moves 0 modes from one site to the other, from one side to the other. Here, I guess, I was looking at this unit cell, for example. It comes from moving this 6 up to here, so the dotted line is the 6 going that way, and the other dotted line is this one. So in all cases, you can see how to do it. So the point is now that sometimes people, and I certainly did for a long time, thought that it was RT that was important. But since your unit cell is not unique, you have sort of a gauge invariance of these properties where you can choose different unit cells, and that's sort of like doing a change in gauge. Okay, so this just shows that we can do the same thing to have a domain wall that couples a system which has zero modes to a side where rather than having zero modes, you have a network of states of self-stress. So the strength of the states of self-stress diminishes as I go from left to right, and the displacements of the modes for the wave function for the C mode, the displacements grow. And you can calculate what they are by taking the differences between the art. Notice that these things, the count does not depend upon the RT anymore, because the RTs are the same for both lattices. And I don't need to bring them in to correct for the unit cell on the surface. So the unit cell here, it's already sort of distorted, so it doesn't make too much difference what I do. So here what we have is on the left-hand side, we have G dot R left minus R right over 2 pi. And over here you have the same thing, but the terminations are different, and you get the opposite sign. Yeah. Okay. I should make a comment now about what happens to the elastic energy. In both of these cases, going from here over to here, we don't have the energy for the bulk thing. These guys are auxetic systems. If you pull, they grow, and if you compress, they go to zero. So the elastic energy is uxx minus a1 uyy squared plus, so you can see that the zero mode is uxx equals a11 uyy, or the other way around, and uxy equals to 0. From this, you can calculate the determinant of Q, and you can see now that when A1 is positive, then we have uxx and uyy have the same sign, which means that you are auxetic. So that applies to this side. If A1 is negative, then you have uxx is minus a uyy, and you get the standard behavior. Now, we can solve this equation for qx or qy. If A1 is greater than 0, as we said, we have a negative +1 ratio, and the RT equals 0, and the determinant of Q goes as Q squared. But when the A is negative, then it actually turns out here that, and I'm now, it starts off as qy squared when I have the qx. So that's just another bit of complication that we have. One thing that's interesting about these states is, most of us come to transitions of the sort we're talking about from the study of phase transitions. And usually when we have a phase transition, we have a change in symmetry. And so what one would look for is, are there changes in symmetry that are signaling the change in the topological characterization, the topological charges of these systems. Incidentally, you can think of this as being a charged system, and the arithmetic for these states is very similar to the arithmetic for polar order in solids. If you want to assign a charge 2, as we did before, to each site, and a charge -1 to each bond, and you can see now, depending upon where the bonds are placed, you can have a topological polarization, which is the charge of the system. Anyhow, these are 3 different versions, which have 3 different topological characterizations, and you can see that these lattices are all, there is a direction, there's a polar direction to them. Here the RT is in this direction, but all of them have the lowest P1 symmetry. You can rotate them around, and you don't end up on top of yourself. Okay, one further observation, which I plugged in a hurry. One thing you'd like to know if you're like me, I mean, if you follow the H-bar literature on this subject, it's sort of magic. You know, they say, oh, all of a sudden I've calculated this characteristic integral, which has topological meaning. It doesn't change when I change parameters until I cross that critical barrier. But the connection between that and the penetration depths and so forth is a little bit mysterious. So here I show you, this is the actual calculation of the determinant of the topological lattices we've been looking at. So it's the determinant depends upon Zx, which is e to the iqx. It depends on Zy, which is e to the I root 3 over 2 qy. This is just representing the projections that have to do with the triangles in the lattice. So this thing is of the form of a constant Zx plus Zx inverse, Zx to the minus a half plus a Zx to the plus a half, and then Zx to that with a 1 over Z on the outside. So if you look at this, you can factor out a factor of Z to the minus 1, and that then multiplies all the rest by a Z. And what you have then is a polynomial, a second-rank polynomial in Zy multiplying 1 over Z. And so that if you do the topological counts, then you can have up to 2 zero modes from the zeros of the polynomial, and one infinity from the 1 over Z. And so from this, you can reproduce exactly what we were talking about without talking about the RTs and the RLs, et cetera. And you can see that you get a difference going in the X and the Y direction. In the Y direction, I have 1 over Z times a polynomial in Z squared. In the X direction, I can take out a Z to the minus a half and square it. So I can take out a Zx to the minus 1. That's this guy. Well, that's the square of Zx to the 1/2. So what I get, let's replace Z by P or something like that. So I have P is equal to Z to the minus a half, Zx to the minus a half, Zx to the plus a half. P squared is Zx to the minus 1. And so when I go through that operation, I have P to the minus 2 times a fourth order polynomial in P. And that then tells me that I have up to 2 states of self-stress and up to 4 zero modes. And that corresponds to the sort of thing we're finding with the multiple solutions to the decay. Okay, so there are many, many other lattices which you can look at. Let me have a class here again. And they have different properties. So an interesting one is this square lattice that's distorted. Now, you would certainly expect to have zero modes in this one on the surface. But in addition, and there what you're doing is you're looking for solutions to C of Q equals 0, right? The determinant of C of Q is equal to 0. So you can have a 0 in the manner that you do on the surface with surface modes, where you have a QY or a QX running along the surface, and which is e to the IQ, and you have this e to the minus kappa r times x or y, whatever it is. And so you have one direction, or if you're in 3 dimensions, 2 directions, which are e to the IQ, x and y, and one direction, which is decaying. But there's no reason why the determinant of Q can't have solutions where all of the Q's are the complex e to the IQ x. And what that does is it gives you zeros in the determinant of Q, which are localized at points in the lattice. And these things move around as we change the properties of this. And what will happen sometimes is this thing will run to the boundary and it disappears and becomes a surface mode. So it's really quite amusing, but it's nasty arithmetic for the most part, because you have to deal with these multiple order polynomials. Another thing you can do is create a topological Hydrochlor lattice. Now, the simple Hydrochlor lattice is a collection of equilateral, four-sided pyramids, and we can distort the pyramids in such a way that something happens. But what happens? Well, I'm in 3 dimensions now. So if I take cuts, I can have zero mode, vial mode images on one plane, and I go to the next plane, it continues. So I get something that might make you think of a vortex line, which is lines of the zeros of the Q tensor or the C tensor. You can make arbitrarily complicated random structures, and these things have topological properties too, which are a little harder to get a hold of. So if you look at the typical simulations for glasses or for sand piles and the like, for the isostatic lattices, what you typically do is to take a large number of sites, and then you put them on under periodic boundary conditions, and you look at the Q equals 0 part of that. So the Q equals 0 part of it is where in your periodic boundary conditions, you repeat exactly the same thing in all of the different cells. But you can certainly define Q and C matrices, and I think now is the signal that I am supposed to go quickly to another, let me see, is it this one? Well, this just shows you more information about the square lattice, that you go from states. Here's a state where I don't have any of the modes. Here, I should also mention that you can have this line of zero modes, and then sort of a zero mode coming out, but they're not quite that. They grow to something else. And so you can imagine that playing around with this, you get a fair number of things happen. Let's see, I guess I'm supposed to, no, I can't, this is a PDF that I don't have the original with me, but you can see the different things there. Okay, this is the one I wanted to look at. So here is looking at the jammed.
Tom, can you put it in full screen?
Excuse me?
Can you put your slides on full screen?
There, I guess I can do that. Can I do that? I'll almost do that, yes. Well, no, I think this is the best I can do.
That's good. That's good. Just to increase the size so that, yeah. Thank you.
Yeah, there is this full screen button, but I've forgotten what it is here. So this is a typical jammed matter thing. And, you can repeat this. So this thing treated as a unit cell in an expanded system which, has many cells repeated in a periodic boundary condition. It has both zero modes along the surface, and it has vial modes in the center. So if we look at N plus and N minus, the green line are the zero modes at the top, surface modes. The orange line are the zero modes at the bottom, and the blue and red is, let's see, does it tell me? Well, they are plus and minus vial modes. And notice when a vial mode appears here, it immediately, I have along the QX directions. So what we found when we're talking about a surface mode, that as we go along the QX direction, and look at what happens to states that decay in the Y direction, then that stays fixed until I hit the boundary of the stability of the given topological cell. But along QX, the number of zero modes remains fixed in what we've seen so far. If I add the vial modes, then as I go along the QX, there's a sudden jump of -1 when I hit the positive blue vial mode. And when we have a red vial mode in, which is the negative one, I see the blue is the negative and the red is the positive. So I get when this comes on, I get a jump in the number of modes, surface modes along this direction, and the opposite around there. So you can see that what this does is it has the property of giving you different penetration depths as a function of distance along Q. And you can move then the bile points around to change the overall number as you go forward. Okay, I think that's enough of that one. Let's see. No, okay, this is just an illustration of what happens with the movie we saw, where you go around, and if you allow the bonds to cross each other, you can complete the circle, but you run into trouble with these things that you can't complete the circle. Okay, oh, I didn't do this one either. Well, this is too much detail to deal with. Okay, how are we doing on time? I'm essentially done here. Let me just check now to see what else I have written down. Oh, yeah, okay, so I have to remember how okay, I'm not going to remember the details of this, but what I want to point out is when we have surface modes, they have to lie in the band gap of the bulk modes. So here, this is for a, oops, I don't want that. I can't move it, that's why. Okay, so let me move this guy. So what I've done is to add next nearest neighbor forces. So next nearest neighbor forces are going to kill the topological modes. And so there's this question you can ask. I have a model, or I have a system that has 2 zero modes on the top edge and none on the bottom edge. Now, when we have a solid, which doesn't have any of these topological properties to worry about, then the two sides, even if you're talking about a system that has P1 symmetry, will have the same number of or types of surface modes. So if I start turning on the next nearest neighbor force, I eventually have to get to a system where I have propagating Rayleigh modes on both sides. So the question is, how does one get to that? And so A is showing a normal state where the red and the blue are the frequencies of the top surface, and the bottom surface is red. And notice this one is a non-topological thing. I've turned on the next nearest neighbor force V, and we come down and we find that we have the red and the blue follow the same slope at near Q equals 0, which is what you get out of the Rayleigh mode down here. And when I go over to weaker, much smaller V, then the zero mode comes in at an angle still, but it never gets to have a big value when I go further up. Now this one,
V is a measure of the next nearest neighbor interaction, or?
Well, what happens here is that since I'm in the non-topological state, then I have modes which, when Q equals 0, if I actually have no next nearest neighbor force, so V is 0, not 0, 0, 1, then these two lines that we see there, they come down and just go along the omega equals 0. So the effect of turning on the next nearest neighbor forces is this gap. and it gets bigger. But it always ends up, because these are, they're types of phonon modes, and they are acoustic in variety. So both of these go down with a slope here that depends upon how strong the next nearest neighbor force is. But these guys match exactly what you would get from the Rayleigh calculation. And of course, when you go further up, you have corrections that come from the fact that you have a lattice. Now, this shows what happens to the case of adding a V to one of the topological ones. So this is the topological state with the V equal to 0.1. So that's large. And what is curious now is we have on the top, we have a blue line that comes down and it meets the red line. And again, they both have the same slope. So we have, and when the V is large enough, we have exactly what we would expect from a normal solid. And we have another acoustic mode that sits up here. So now what happens when I go from large V down to smaller and smaller V? Well, as you might expect, these lines have to start coming down closer and closer to zero, because we know that when the V is zero, we have only the two zero modes on one side and none at the other. So the blue line gets shorter and shorter, and when I have the V equal to 0.001, it's just this teeny little blue thing at the bottom here. It dies when it goes into the continuum. So here, the red lines, the two red lines are there. They're there even in the strongly non-topological case. They all move down towards the origin, but as long as I have this little bit of blue space down here, this guy is not a zero mode. It dies in the continuum of the bulk states. So this is how the system learns how to go from the topological, where I have zero modes, which can either be two on one side and the particular surface we're looking at, or one on each side. And then we turn on the V, and what happens is these things move up a little bit. The blue line separates what grows longer, and the red line here crosses, and everything works out the way it should, which I was happy to see. Okie doke. Let me just see now if I had something else I was going to. This shows the more complicated version of that, and lots of them. We played around a lot. This is just showing the types of things, lattices, that might work out for you. And this shows, you know what this is? Does anybody know? It's part of a jet engine that was additively manufactured. Okay, I think I have again come off a little short, but it is just a few minutes until the end. It's probably, I'm willing to answer any questions that you might have.
Okay, thank you, Tom.
Yeah,
Are there
there's a
any
lot to cover.
Say that again.
It is a lot to digest, unless you've seen it before.
Are there any questions? I do have a question about the disordered lattice that you considered, for instance.
Yeah.
And when you do the topological characterization, I suppose you do for a finite system, and just calculate explicitly things like the compatibility matrices and things like that.
Well, we then take the trouble to ask the question about whether that, basically what we have now, under the periodic boundary conditions, you have a large unit cell, as large as whatever the spin glass, but the jamming people look at, hundreds if you wish. And so that you can, for that system, calculate things where that large number of things is a unit cell, and it gets repeated. And so I can talk about the unit cell, this being a periodic lattice.
Oh, I got it. I see.
Large unit cell.
I see.
So there are two things that go on. One is to study that, where it just shows you get more and more soft modes. But then in particular, what is the goal of the calculation of the jamming people is the Q equals 0 part, which is the unit cell itself. Right, and you can go through and you know, see that they do obey what they should obey in terms of keeping straight the zeros and self stresses and all of that.
I got it.
You know, you can also do it. Let's see, did I have that here? No, it's not that one. Shoot, I don't think I can find it now. Well, okay, so I you know, I've lost the lattice, but it's, you know, you can do quasi-crystals, and you can do, and Xiaoming may talk about her work on the quasi-crystal stuff. And, you know, you can do all kinds of other things. I should emphasize one thing here. I have focused only on these zero mode things. So unlike what goes on in the quantum things, you know, there's no defined zero of energy there. So you can move that all around, and the treatment of what goes on at zero energy is not too different from what goes on if you have you know, a band gap at higher energy. So this is really different from what most of what other than, I should say, this has close ties with the Schrieffer-Heeger model and variations of it where you stack the polymers. But it doesn't do the sort of things that go on in the topological graphene. But you can have band gaps in phonons that occur at finite frequency. And those look a lot more like what goes on in optical systems and in the electronic systems. This is sort of a specialized field, which has, I think, a lot of interesting math in it, at least.
Okay, thank you, Tom. Let's thank Tom again. And we'll come back at 2 p.m. Have a short